Welcome everyone to the 2022 edition of TriStar, our second virtual version. Hopefully next year everything will be back to normal and we'll be meeting in the Corey building like usual. My name is Tom English, Director at Klein Observatory here, and I've been helping put on these events for a couple of decades. And I know many of you who have already signed on have been to many of these TriStars, and we appreciate that. A couple of announcements. The Astro Imaging Contest, there's a link to it on the TriStar website. I'll put a link in the chat in a little bit. If you're planning to participate in that, you need to go ahead and get your images loaded up. I think the deadline is noon, if I remember that right, to get those in, and then voting will open shortly after that, and then we'll announce the winners after the last talk. So I'll put that link in the chat. I'll also put the links to the other talks. They're also available at the TriStar webpage. If you just use your favorite search engine and look for GTCC Observatory, you should be able to find our observatory link, which has a banner on the front page that takes you right to the TriStar page and the schedule with the links to the talks. If you received a notification with the links, just use that email. But we've got 4 good talks for you today, one coming up in just a sec, and then another one this morning before lunch, and then 2 in the afternoon. I should also mention that coming up on our calendar, we have on April 1st, our Stellar Society lecture. It will be Paul Byrne from Washington University, St. Louis, formerly of NC State. He's going to be talking about Venus. We'll get the details for that on our website soon. And then looking ahead to next September, our Fall Astronomy Day lecture, we've arranged for Emily Levesque to give a talk. You may know her book that she has out now, The Last Stargazers, but she studies massive stars, and so we're looking forward to that. Look out for more information about that on our website as well. But today, we'll focus on TriStar. And our first speaker is Jason Ybarra from Davidson College. He's new to North Carolina astronomy, started up at Davidson, I think, this past fall. And he is, in his regular astronomical research, he has studied star formation in galaxies, but he's also really interested in the history of astronomy. He has, for a long time, edited the This Month in Astronomical History series that the American Astronomical Society puts out. He's active in the Historical Astronomy Division of the AAS, and one of the articles he wrote for the This Month series was about the observation of Algol, and he's going to share with us the background on the star that represents the head of Medusa. So let's turn things over to Jason and hear about the Demon's Head.
All right, thank you. Hopefully my presentation is showing up. Okay, good. Well, thank you, everyone. I see that there's a meeting chat, so definitely throughout, if you have any questions, please use it. I want to make this as interactive as possible, even though we are online. So I'm going to talk about Algol in a historical context, because just as Tom said, I'm interested in the history of astronomy and what we can learn from the history of astronomy. So many of you know already that Algol is, a well-known variable star. In fact, it's not a star. It is a star system, in particular to the 2 main components of Algol, eclipse each other over time, and you can actually, it's one of the few stars that you can actually observe actually dimming during an eclipse. So it's typically about a 2 magnitude star, pretty bright, and then it's going to go down by almost a magnitude and a half during its eclipse. So this is approximately 4 hours. And it's a little less than 3 days is that period of eclipse. And it's oftentimes referred to as the demon star, the demon's head, the winking star, and because of that, it's been suggested that early stargazers observed the changing brightness of Algol, although that wasn't referenced anywhere. And Algol typically has been, called the eye of Medusa, the eye of the Gorgon, but if you look in the historical documents, you don't really find that. So we'll talk about that. It's very difficult to begin any astronomy talk with history because ever since, I'm sure we were able to look at the night sky, astronomy has been part of the history of our species. So I'm just going to start with Ptolemy and his star catalog, which in part he inherited from Hipparchus. And in it, he references the constellation of Perseus with the various stars in Perseus and their magnitudes, and then references the Gorgon, the brightest star in the Gorgon, giving it a second magnitude. The Gorgon in Greek mythology is very different than oftentimes the Medusa that is often represented in culture, and that's due to the Roman aesthetics of Medusa. The Gorgon was a pretty frightful creature. In fact, the Gorgons were 3 sisters and may have represented some earlier triad of goddesses, of which Medusa was the, at least, within the framework of mythology, the only one that was mortal, which, in order to make Perseus the hero, she had to be mortal. But as we can see in some of these very early 4th century vases, that the Gorgon is a creature with boar's tusks, tongue out, oftentimes, thought to represent death, and, snakes as belts, and as we can see, snakes as, inherent winged creature. This was the Gorgon, and that's the one that Ptolemy said, okay, the bright star in Gorgon. Now, Ptolemy, introduced a lot of, the writings of Ptolemy introduced Greek astronomy to the West via the Islamic scholars of the time. And unfortunately, along with the star catalog, we got the Ptolemaic model of the solar system with its various epicycles and deferents and other things that came along. But so, fortunately, I'll just go ahead and focus on the star catalog. And so Ptolemy's catalog was was in his Mathematica Syntaxis, his treatise on knowledge, which eventually became later known as the Great Treatise. And that, in early times, 9th century, 8th and 9th century CE, was being translated into Arabic. And from that, we get Al-Sufi's The Book of Fixed Stars, where he takes a lot of the catalog of Ptolemy and also includes his own references. Well, as that happens, the Gorgon becomes the head of the ghoul. So Ras Algol, and here is an 11th century copy, we think 11th century copy of the Book of Fixed Stars, showing the representation in the Arabic copies of Ptolemy's book and also of the Islamic scholars of the day, where Gorgon becomes the ghoul with its hairy beard, now is apparently male, and this is the representation that became part of how eventually Europe first saw Perseus in the constellation. So I can just show you some Latin translations later on, showing actually the old ghoul imagery. So Latin translations of Al-Sufi's catalog. We even have Latin translations of Ptolemy's catalog, also keeping this is a early 15th century copy, keeping that ghoul imagery over time. And this is a Latin translation of Ptolemy. Okay. Now, in 12th century Spain, right, there was a lot of collection. There was a lot of scientific books from Islamic scholars. They were all written in Arabic, and through that time, there's a lot of translating happening. And in particular, Abraham Barria, in Latin, Zavazorda, translated a significant number of Arabic books into Latin, but he wrote his works in Hebrew, essentially pioneering the Hebrew language for scientific purposes. So previous to that, Jewish scholars actually wrote most of their work in Arabic. Arabic was like the Latin of the time. But at this time, Hebrew started becoming a language for scientific purposes in Spain, and Ras al-Ghul, the head of the ghoul, became Rosh Hashed, head of the demon. In the translations, sometimes Rosh Hasatan. He's also, by the way, responsible for introducing the quadratic equation to Europe. I don't know if we should be thankful or not about that. 12th and 13th century Spain was actually, for scholars, just wonderful. There was a lot of cooperation between Jewish, Muslim, Christian scholars, translations of the works of Arabic, many of those from translations from Greek, when were translated into Hebrew and then into Latin. Some directly went from Arabic to Latin, some went from Arabic to Castilian to Latin, and then from Latin to the rest of Europe. This was a time of a lot of scholarship. that was happening. And so this is how many of the works that we know from antiquity came to the knowledge of Western Europe. Because of some of these pathways, we have the head of the demon becoming the name of that small constellation of 4 stars. And that's where we end up having and getting the demon star from that. All right. So a little after this, and the reason I bring up Gutenberg is because spreading knowledge was pretty slow beforehand. Books were hand written for the most part. Oh, I have a question. With all these translations, how much was lost in the translation? That's a good question, and sometimes there are fragments of at the actual Greek sources, and so we can go and look back at the Greek sources and see that, and be able to compare. And I don't think much was lost necessarily, except for errors. And there's a lot of Greek work from antiquity that nothing survives, and we only know about from these translations. So that I don't know. Gutenberg's printing press revolutionizes Europe, really, in a way. This led to increased literacy. The scientific communication, started blossoming in a way that beforehand it mostly were letters, and now we have journals. Knowledge is being spread around. We have an increase, actually a development of a middle class in Europe. And as people start reading, perhaps for the first time, many start realizing something. For me, it's obvious. I wear glasses, right? So the need for glasses became a thing because of the printing press, right? When you start reading, you're like, oh, I can't see this, right? So lenses, in fact, the technology for glass got better and better, so glass could be made into lenses. Much of this was done in Italy. So now we have a whole field of lens makers making lenses. And here we have, in fact, there's some simultaneous inventions of the telescope, but here is one representation of, I think it's Lippershey, of the telescope, a lens maker observing children, this is the story, holding up 2 lenses to make something closer, to see like a distant weather vane appear closer, and of course takes that idea, I don't think credits the children, and invents a telescope, or the telescope. And information, now remember, we have the printing press, gets very quickly to Galileo. Galileo makes his own telescope, shows it off, and also decides to, hey, we can see a lot of things closer, and we can see the enemy coming, but let's look up in the sky. And he looks up in the sky, and he sees a whole slew of wonderful things. That the moon has craters and a rough surface. It's not smooth as marble in the Ptolemaic and Aristotelian kind of versions of the universe. The sun has things on it like sunspots actually going around the sun. So this, the perfect immutable universe idea is definitely going away. In fact, there are things that definitely don't orbit the Earth, right? Galileo observes and discovers the Galilean moons of Jupiter and observes them over time. So, there's a lot happening. And with politics of the time, Galileo got in trouble. We all know that. And, had to step back and profess that he's not really talking about a universe that, especially the Copernican model, which he became known for representing. But Galileo, in addition to all of this, was an experimentalist. And that is one of the, what I would say, very important ideas that Galileo had as a scientist and as the field of science, right? Making observations and using those observations and testing those observations to understand, right? Understand our world, and also the importance of mathematics and being able to describe these things. So Galileo, has various laws of motion before Newton. But as things go in Italy, you had to be careful about your observations. But this idea of making observations as a basis for science was very important. And so at some point, right, late 17th century, we have an astronomer, mathematician, lens maker, Renaissance man, as most scholars were during the day, succeeded Montanari, succeeded Cassini as a teacher of astronomy at the University of Bologna. And part of what he did was start, making very careful observations. Had to still be very careful and make sure that your observations were perfect, were good. And he observes around 1667, he's pretty sure he sees the change in the bright star within the head of Medusa, what we know of as Algol. Sees it dim, right? Then also sees it become brighter and then dim again. But note, these are many years in between. And we know that Algol's period is like a little less than 3 years. So what was happening? Well, because it's a non-integer time period, and also with our orbit around the sun, catching an eclipse randomly, and I gave you this problem to my students in math methods, is not as easy, right? You have to catch it relatively right, and you may not be looking at Algol every night. You don't necessarily expect a short period variable. At this time, only one variable was known, Mira. That's a long-term variable. So the idea of a short-term variable wasn't even there. So there wasn't necessarily any reason to be observing over time. And in a period, for example, of 30 days, you typically have 3 to 4 nights you may be able to observe an eclipse of Algol at night if you observe all night long. And this is in winter. So your time frame of just randomly catching this is not as good. And so in some ways it becomes less surprising that it took, almost 112 years later to actually have a determination of the period of Algol. And we have two neighbors, Goodricke and Pigott. They went out and actually decided to observe as many variable stars as they could in a very systematic way, night after night. And still, it took observing Algol for about 5 months until they were able to determine the period. And Goodricke submitted a report to the Royal Society of London detailing their observations, reported the period of variability, and in fact postulated perhaps there was something revolving around Algol that caused that dimming, which was great. Because orbits, or the idea of orbits, right, after Galileo, became a thing. Some of that came about because a few years earlier, Newton has this idea. Newton thinks that maybe what causes stuff on Earth to fall via gravity is the very same thing that keeps the moon in orbit around the Earth, and does some calculations on that. And thus, we have Newton's law of gravitation associated with Newton's laws of motion, and it's called universal gravitation. It's that we have something on Earth that's gravity, and that's actually everywhere. And that is what keeps our moon in orbit. It is, with Newton's laws, the forces of gravity, the force of gravity between the Earth and the moon are equal, as far as the force that the moon pulls on the Earth and the force that the Earth pulls on the moon are equal, opposite and equal, but the effect is different because the Earth is so much more massive that it seems as though the moon is going around and orbiting the Earth. But in reality, they're orbiting the same center of mass because of that. And so two systems gravitationally interacting are going to have a relationship between their periods and the distance, the semi-major axis between them, and their mass. So observing the period's nice, knowing the distance between stars, a little more difficult. Some binary star systems are visible binaries, visual binaries, and you can observe them over time. If you know how far away they are, you can start getting a good estimate. Yes, so there was a question about, there were certainly many observations of Algol between Montanari and Pigott, but there weren't systematic studies to actually determine that relationship, that period. So I think that was, what I would consider Goodricke's and Pigott's, contribution to astronomy, to the study of variable stars, that systematic observation. It wasn't only Algol that they observed and were able to start pinning down these periods. So we have a relationship of the masses, right? By this time we have the gravitational constant. We just need to know how far away they are. Now the nice thing about Algol and stars like Algol is they orbit each other and go in front of each other. Now that at the time, at least, of Pigott may not have been important, but spectroscopy in the 19th century became a thing. Looking at the stars' spectra, looking at the spectral lines, and then we have relativity, and we can see the shift over time of these lines, and that shifting, the Doppler shift of these lines, tell us something about the speed over time. And now that we have radial velocity information, and if you have radial velocity information and you have the period, which is time information, that gives you distance information, right? From introductory physics, right? We know speed is distance over time, so now we can get the distance between these stars that make up this binary system, and also their proportions, which is important too. So it was thought that Algol was an eclipsing binary, and basically in 1889, even though no one disagreed with that idea, it was actually shown, right? The radial velocity measurements of Algol showed that the idea of what an eclipsing binary is was there, and then the study of masses, learning what the masses of stars are, became a real thing. And Algol type variables, one after another, were started being observed. Maybe the initial estimates weren't that good. Here's one of Beta Lyrae, little overestimate there, but this was the beginning, right? The eclipse theory was, for the most part, confirmed. With spectra, and looking at the spectra of stars, and for the most part, if you think about what was happening in the late 19th century with the spectroscopy, was let's just observe as many star spectra as possible. And they look different, right? Each star has slightly different spectra, but you can kind of classify them, and so they were classified. Interesting story there also. I won't go into it, but by the time Cecilia Payne comes around, we have these classifications of stars. There were hints that they may represent perhaps different temperatures just based on their color, but she showed, right, she went ahead and did the calculations to show that spectral types do correspond to surface temperatures. She also showed, with that spectroscopy, that stars are mostly hydrogen and helium. The sun is mostly hydrogen and helium. The ratio of metals in the sun actually represents very similar to the ratio of metals found on Earth. So incredible, probably one of the most important theses, I would say, in astronomy, but in the 20th century, maybe all of it. So this is nice in a way, because this is more information about a star. We have ways to measure the star's brightness, right? We can measure, we get an estimate of its temperature, surface temperature, and with binary stars, and specifically these eclipsing binaries, we have mass information. You can do a lot with this. For example, 1938, the first mass luminosity relationship was designed. or not designed, that was plotted. There's enough information to actually kind of plot it and see, hey, there's what seems to be a really true relationship between mass and luminosity. And there are perhaps even different types of stars based on where they are in this mass luminosity relationship. So we can see stars down here with very, relatively lower luminosity, says, representing white dwarfs. This is from the 1938 paper. Algol is, I think I have a slide out of place. I'm sorry. So I have that at, we can't actually measure putting a star on a balance. That's why eclipsing binaries are important. Now, observations over time of the period show that there are variations of the period of Algol's eclipses. And what is causing them? That has been a question for a little more than maybe 140 years. There were short-term variations in the period, which are due to Algol C, which is a third component very far away from the Algol binary. But there's other variations over time that are hard to explain. One of the most popular explanation are due to kind of magnetic cycles that can cause a torque. If that's true, then the possibility is that depending, it may be more of a chaotic period variation. It would be really nice to be able to measure all the way to when Montanari, because this starts off with Pickett's observations, right? We have 100 years earlier, starting with Montanari. What was happening then? If we knew what was happening then, maybe we'd even have a longer baseline of information to do this. We don't know, right? Montanari wrote years. Like this year, he observed that. His notes weren't kept. However, early 19th century, astronomer Porro found Montanari's student Bianchini's notes. And Bianchini went ahead and copied Montanari's notes into his own notebook. And so this was presented as some of the, at least from 1670 to 1681, these are observations that Montanari made of Algol, just copying into Bianchini's copying into his own notebook. The problem is there's a little bit of inconsistency here and there with Algol's known period. And what was Porro doing? And I'll show you, because I have a research project on this. Right? This is what Porro had to read. Right? These are handwritten notes from Bianchini. This is Bianchini's. This is an image of Bianchini's manuscript that's in the library in Verona, and there may have been a copying error from there to here, and I believe there is, and hopefully in the next year or so we'll have a paper out on that reduces that inconsistency. So that's what's next, at least for me, for the story of Algol. Last year there was and observe. Well, there was a study that took this period, what seems to be like a periodic change in the period, by astronomer Jetsu, and hypothesized, I think, like 5 extra stars to the system. That I think that requires caution. So, okay. Well, I'll end here. The study of Algol, the system, even many of these astronomers, Goodrick and Pigott. I mean, this is just, there's so much, and it's very interesting. So I hope I was able to just provide a little bit of background into Algol as a star. So thank you very much. And of course, if you have any questions, please go ahead and let me know. Type them into the chat. I'm easy to find also via the internet, so you can also send me an email.
So add your questions to the chat. I'll put a couple of meeting announcements there in the meantime also. So I have one in the, while we wait for other people to type in. Other cultures, how widespread was the winkiness of Algol recognized in the past?
Yeah, there are no explicit, I would say, statements of that. So there was an analysis of an Egyptian astrological calendar that went over time to kind of like go on various days throughout the year. I think it's called the calendar of lucky and unlucky days. And it seems very random, but there was a numerical analysis of this, to see if there's any pattern in the randomness done by Jetsu also. And in there, of course, pattern they found, kind of the 28-day cycle of the moon, but there was also like a 2-day-ish cycle or so that would seem maybe to match Algol. So there is this possibility that the Egyptians also, in their observation of the night sky, observed that, and it became part of their kind of astrological calendar, even though there was no explicit statement about Algol's dimming. I do believe. So I see why. Oh, why is Batman's nemesis Ra's al Ghul named after the star? I just think because probably it sounds cool, right? How many people? Oh, I don't know. I've tried. Well, I've tried to observe it with my eyes, which has not been successful.
So, can people do the raise hand to indicate if they have seen it? I don't know if all participants can actually do that.
See some.
They should be able to.
Okay, so if you see the little icon with the emoji with the hand up, if you've seen Algol at minimum, just raise your hand. So we see a few of them there. you're right. It's tricky. You have to. It's hard to wander into it, and typically you can maybe see it 2 cycles in a row if you start paying attention. But it's really easy to just look and look and look and see it bright over and over and over.
I think what's the best way to see it? There are calendars. There are calculators online that will tell you roughly when it will be. Some are better than others, but I think there's an online one by Sky and Telescope.
Yes, Sky and Tel has a good one. They used to have it regularly in the pages. I think the observing editor is actually watching this talk, so she might be able to tell us if it's still regularly listed in the pages. I always use the website when I'm looking for it. Which other stars did Pigott and Goodrich observe in their observing program?
I don't know. I think those two references here
papers
really
will tell.
will
I have the impression maybe Delta Cephei, and maybe there's Star and Aquila maybe that they had done. I don't know if they did Beta Lyrae. It seemed like they had looked at several.
Yeah. I'm sure they observed Beta Lyrae because that was one of the soon after Algol's discovery of its variability. I think Beta Lyrae was there, but I don't know. Are there exoplanets around the Algol system? I'm sure there are, because in my understanding is probably all stars have some sort of exoplanetary system going on, whether we can observe it or not. If Algol, though, and even binary systems have shown to have an exoplanet. So Algol has 3 known companions. And we have the binary and with a third companion on the outside. So the stability of orbits, and if Jetsu's paper is correct, and we have all these other stellar components, I don't know if the gravitational interactions would keep them in the system. But that's just wild guesswork on my part.
So Diane has come through for us and provided the link to the online tool for observing the minima and verified that it is definitely in the pages. So thank you.
I don't know off the hand, personally, with the spectral types of Algol. There is a thing called the Algol paradox, which you may be interested in looking up. But because there is mass transfer, that kind of messes with the observations of spectral types and our understanding. So that's always to be careful about. One of the stars in the Algol system, right? It's a large red giant, and materials flowing onto the other system over time, which is perhaps colluding spectral types as far as our understanding of them in the HR diagram.
So last call for questions. Anybody else got anything they want to ask? And I'll echo that note from John. Thanks, Jason. This was great. And I did put a link earlier in the chat to your article for this month in astronomical history on this topic. And so those of you who follow through to that link, you can explore some of the other articles in the AAS's series this month in astronomical history. Our speaker has been the editor of that series for quite a while and has several other contributions there. So check it out.
Thank you, everyone, for being here, especially on an early Saturday morning.
And thank you for speaking with us. This event happens every spring, so we hope you'll be able to come up and see us in person in the future. Let me do a couple of sort of housekeeping things here before we tune out for this session. Remember, the astro imaging contest is going on, so if you want to submit some images, you should be doing that now. Voting will start a little bit later. There's a link in the chat here, and the link is also on the TriStar page. And if you received an email notification about the meeting, there should also be a link that can get you there as well. Our next talk starts at 11, so we have a little bit of a break here. The next talk is Dr. Jessica Noviello, who is a planetary scientist, who's going to tell us about cryovolcanism, which she says is the coolest geological process in the solar system. And believe me, when you see her talk, you'll definitely think that as well. So come back at 11. It's a different link, so hit the website and go to the link to that talk. Come in at 11, and we'll explore the outer solar system. Thanks.